So here's our talk title. Some of you may recognize the logo. I'm going to try something new. I've never done this before, but we're going to play a little bit of music for a few seconds, and I want you to clap. James is going to give you a signal. If you've never heard this song before, hopefully you have. If it plays. Play. There we go.
No one told you life was gonna be this way.
Yes.
Just a joke you broke.
Yes. Brilliant. Oh. Oh.
That was the second most nerve-wracking aspect of this talk done.
That's the worst.
Out of the gate strong. So my name's James Henry. This is the legend that is Todd Motto. You might know us from our work on Ultimate Angular, where we produce Angular and TypeScript courses. You can find us on Twitter, Mr. James Henry and Todd Motto. We both love contributing to other developers' work. I work on ESLint and Prettier, and Todd has been educating the world via his blog, toddmotto.com, and Ultimate Angular for a number of years now. There's our fancy logo.
Here's our pretty logo. Oop, wrong way. There we go.
So Todd is going to start you off by talking about a lot of the concepts that we wanted to cover today. We're thinking about imperative and reactive programming. These are not particularly obvious terms a lot of the time, and Todd's going to take you through some concepts, and then I'll walk you through a code example together.
Yep. So hopefully it's going to be a good ride for you. We've got some Friends things in there as well, so any Friends fans? So we're going to be talking a bit about reactive thinking, how we can start to think reactively. We're also going to discuss imperative thinking. There's no point kind of just going to the end goal without looking at the beginning. Now, what I want to cover to actually get us there is the design patterns behind these. So you may have come across something that looks like this, and I remember you look at it and you go, what is that? And you end up looking a little bit like Joey when you talk to your friends about RxJS, perhaps. Like, yeah, I know what this stuff is. So today, we're going to make you not laugh like Joey, and you're going to be confident in talking about it. So these are the two things that I want to talk about, and then I'm going to hand over to James. So I want to talk about the observer pattern. When we deal with RxJS, we typically use observables. Angular has, obviously, a lot of its core is based on observables. And then we're going to look at some sequences and some operators. So first things first, I want to talk about the observer pattern. We're not just going to go into, these are very conceptual, so we're not going to just show you loads of code and hopefully not confuse you. So what I'm going to do is take a light switch. This is the coolest light switch I could find on Google. They are all boring. So we all probably worked in an office. You walk in the morning, and it's pretty dark in there, and you turn the light switch on, and all of a sudden, you're greeted with a brand new office, which looks way better. But it's got that instant, and everything is just on at once. So what I want to talk about is some of the theory behind the observer pattern and how we can kind of think of it as just light bulbs and a light switch. So if you imagine we've got our green box here, which is just a light switch, and we've also got some light bulbs. So we can obviously go to the shop, we can buy 3 light bulbs, but we want to put them in the roof and connect them up somehow. So if you imagine we just connected our light bulbs to the switch. Now, in a programming sense, this would be a subscription when we think about RxJS. You've probably seen subscribe, and that's where you're asking for that particular piece of data. So you can see here that we have the subscribe, and we're asking for the green box, and we're subscribing to the green box. And each of these purple little boxes, which are the light bulbs, are passing themselves in as an observer to the subscribe. Anything changes, they will all get notified. So if we turned our lights on, all the lights would go on. If we turn them off, they would go off. They're all wired up. They're observers. They do nothing else. They don't go to the light switch themselves. They don't have a switch on them. They're simply waiting for a switch on the wall, and then they're on. So let's say we've got 2 blue boxes. These are some new light bulbs that we've purchased. And all we need to do, again, is we can just simply put them in the same room. And this makes it quite easy to think about how the observer pattern actually works. So now we've wired up 2 more light bulbs. We can then add it essentially to the same source. We've got subscribe on the left and subscribe on the right. Now, you've probably seen these terms, observable and observers. So the observable will be the source. It will, for instance, with our light switch, it could emit an on event, could emit an off event, and every observer will respond to that accordingly. Now, I've put question marks inside of these because that's pretty much the theory behind it, the basics of the observer pattern. It doesn't matter what it is. Typically, we have a producer, which just produces values. It can produce them constantly. It could produce them over time. And our consumers, they just simply get given the data. So we call this the push and pull, or the push model, where basically the producer would push down to the consumers. So they just simply ask for it if and when it's given to them. So let's move to sequences and operators. So these patterns are going to set James up, and we've got a lovely orange ball, which is a mystery of what it will be for. So sequences and operators, you may have heard the term streams or whatever buzzword this week. So I want to kind of use the example of coffee to talk about these sequences. So by now, we've understood that we have some kind of producer. It produces values. Once it's done, we then consume the values. Now, if you think in terms of an Angular application, for example, the producer could be a routing param subscription, and we just simply listen to it, and we can change a component's data based on that. So that's an example. Now, somewhere in the middle, because we are talking about the sequence of the observable, we're going to call this the pipeline. Doesn't need to be one, it could be two, so we've got two blue boxes. When I started with RxJS, I came across these, map and filter. So you've probably seen these before in the RxJS documentation, or even on the Angular documentation. So these typically make up what we call a sequence. So we can have a producer and our consumer, and somewhere in the middle we can transform those values. So this is just trying to think about the different parts of it. So we got produces values, business logic, we'll call it in the middle. It's important to note that they're just pure functions. So an observable sequence can just be a pure function. It has an input, and it returns something based on what the input was. And then we have the final outcome. Bit of a Friends reference. So back to the coffee example, how can we think about sequences in terms of coffee? Stay with me on this one, okay? So let's imagine you've got a coffee machine at home. Someone's bought you this coffee machine for Christmas. We can say that we've got a water, and the water in the coffee machine is, we've heard the term stream, so it literally is a stream of water. And that water will be just given and given and given. So let's assume that we want to make 2 cups of coffee at the same time. I've got 1 cup, 2 cups, and I put them underneath. On one of them, I want a white coffee. On the other, I want a black coffee. So we've got the water, and it's just giving both of our coffees these values. We've got the water. So the next step in the sequence, I actually want to heat the water. I don't want a cold coffee. That would be bad. So I want to call this function heat water. After this has been completed, I want to add some beans to my coffee. Now, the difference between these is that the one on the left is a white coffee. So I'm just going to add some milk to it. And the end result is we end up with a white coffee and a black coffee. And this is kind of a good idealization for whatever the word is for imagining how a stream works. So we have the water, it's continuously given, and it's up to each coffee cup we want to decide. So I might press white coffee, I might press hot chocolate, and it's going to add cocoa powder. So essentially it's the same stream, and we can do different things, and we get different outcomes. So I've split these up again. So we have our producer, which is our water. We all start with the water. We can then heat the water, add the beans, add the milk if necessary, and that part is the business logic. So we start with the water, it's not business logic. The coffee cup at the end isn't business logic. We just consume it quite literally as a consumer. So for this, we're going to imagine taking the previous diagram and actually turning it into some fake code that might be running inside of a coffee machine. So typically, an observable might have a dollar suffix on the end. So we could say this is going to be an observable. This is just a naming convention. What we could do at this point, the first argument that we get is, in fact, the water. Now, you can ignore switch map for a second. So we first get water. We then have an arrow function. I know it doesn't have an equals sign, which then calls a function called heat water. At this point, we take the argument and we pass it into the heat water function. And we need to do this because this is now our observable sequence, and we need to know when that heat water has actually finished. We don't want to keep heating the water forever, and the coffee machine may explode. Now, the interesting piece is the switch map. So when that's actually completed, our heat water function, we're actually going to get the result from the heat water, and we're essentially going to switch to a different stream or a different observable. So we're actually going to get the hot water back. We're not just going to get the water that we started with. So we're switching to the result of the heated water. So at this point, we've got the hot water, and we want to add the beans. We're going to pass the hot water in. The coffee machine can mix everything up. So at this point, again, we're doing another switch map because we want to know when all the beans have been added. We don't want the cup overflowing with beans. And at this point, we get black coffee. And in this example, we're going to add some milk, and we're going to pass the black coffee in as the function argument. When that's all done, we then have our consumer, which is the resulting coffee that we wanted. And in a subscribe, you want to do something with it. So at this point, I'm just going to say, I'm going to add it to my cup. And that's the coffee analogy in terms of streams. So now that we've covered the observer pattern, the sequences and operators, when someone asks you about RxJS, you can be Joey, how you doing? Now for the ball.
Now it's the most nerve-wracking part of the whole talk.
This throw is a fear.
In order to blend our seamless transition from one side of the stage to the other, we're going to distract you with a shiny ball, and it's going to be a reminder of this particular Friends episode. This episode was based entirely around the fact that the friends were throwing a ball around, and the whole game was just not to let it drop on the floor. We have already lost this game, but for example, if I drop the ball, the game is now over. Now, this is a lot of fun, but obviously we're developers, so we love to take fun concepts and ruin them by writing code. So that's what we're going to do now. We're going to think about this game in terms of how would we actually program this, and fundamentally we're going to look at what would it be like if we did it in an imperative way, and what would it be like if we did it then again in a reactive way. So here comes a demo of what it looks like when you turn what you just saw into an application. It's probably the best thing I've ever made, and I will be starting a Kickstarter fund to productize it.
We're seeking investment for this game.
So as you might have noticed, Todd and I get on really well with the Britney mics because we love gesticulating. So it was actually really easy to find previous talk photos of us both ready to catch a ball.
I suppose.
So we're all ready to receive the ball. Hopefully this page is refreshed. And basically we need some kind of event to start the game. So I've arbitrarily gone for a start button. So when I click the button, James gets the ball, he throws it well, and Todd's dropped it. Let's play that again. That didn't last very long. James throws the ball. It's a good throw. Todd catches the ball. Good throw. I dropped it. So basically, there's a little bit of probability built into this to randomize the fact that we suck a bit at throwing and catching. And we'll try and cover the core concepts of this little application in this talk. So that was the demo. So first of all, we're going to go for imperative. Now, in this talk, we're not saying that there's a black and white binary. Imperative is bad and reactive is good. Reactive's not some holy grail, but there are always different ways to approach the same solution. Like we have solved this app. We have fulfilled our brief of turning this game into an application in two different ways, and they both work. But there are certain aspects of, for example, the reactive one that might make its ongoing support and our ability to add features a bit more scalable. So fundamentally, obviously, we're dealing with a little web application. So the elements of our game are turning Todd and I into divs. And the ball is a div, and there's a start button. So try and keep up with those 4 moving parts. There will be quite a few things to keep in your mind on the slides, but we've tried to boil it down as much as possible. Something just to bear in mind across both examples of imperative and reactive is that we have just a couple of helpers involved. So we have this add ball function and remove ball function. That just handles making the ball disappear from me and appear in Todd and that kind of stuff. So it doesn't matter about the implementation details of that. It's not relevant. And then we have the exact mathematics of how likely it is that one of us will do a bad throw at any one point. And importantly, we use that information to inform how likely it is the other will catch it. If I do a throw over there, it's much more likely that Todd's not going to catch it than if I throw it perfectly to him. So we kind of got 2 elements of probability in there. The exact probabilities are not really relevant to the example again. So effectively, we have 4 to-dos in this imperative example. We want to start the game from clicking the start button. We want to throw and catch the ball between us. And then we want to build in the fact that we need to check if a given throw was good or bad. And then when it arrives at the other side, we need to check, based on if that was a good or bad throw, did I catch it? So starting the game, really simple. We're just going to be attaching a click handler to the button. So we're just going to have a function called handle click, and everything else we cover now will live inside this handle click function, where it says our game code. So we've done the first thing. Amazing, amazing progress. We're racing through. It gets a little bit more involved when we think about throwing and catching the ball. So we're going to boil it down to, we have this one function called throw and catch between, and it's going to take 2 people, 2 DOM nodes in this case. So we're just going to throw and catch between James and Todd. And that's our usage. So this is going to live inside our click handler. But then we're going to define the function like this. We're going to have person 1 and person 2 being passed into the function. And the key thing is here, we're going to have to make it call itself so that we can keep the ball going backwards and forwards in our game. So at the end of the function, it's going to call itself, but it's going to swap the arguments around. So if James is player 1 on the first call of the function, it's going to swap it around, and Todd will now be player 1. That will help us minimize how much code we're having to duplicate throwing backwards and forwards between us. After we've covered that, effectively what we have left to do is we need to make sure person 1 starts with the ball. Then we need to build in the fact that there'll be a little bit of a wind-up while we throw, and then it'll travel through the air, and person 2 will hopefully catch it. So nice and easy. We've got a helper function, add ball to person 1. Then we remove the ball from person 1 as it flies. We add it to person 2. And then we go back again. We just keep calling that function. So right now, we've just built in the way to add and remove the ball from the 2 players. However, this is effectively like saying that we're superheroes who always throw perfectly, and it takes us 0 milliseconds or a fraction of a millisecond to throw the ball between us. So realistically, we need to build in some human nature to this. So all we're going to do, because we're dealing with this imperative form, we're going to have to define our set timeout to delay the fact that it takes a second before we throw the ball. So we're taking the exact same code, but we're just indenting before we've removed the ball from player 1 inside a set timeout, and that's just going to be 1 second. We have to do exactly the same thing before player 2 receives it, because the ball's going to fly through the air for a second. So we've got 1 second, catch. So it's still pretty straightforward. It's still pretty easy to deal with. The rest of the function is all still the same. So we fundamentally dealt with how would we create a perfect game between people who never throw badly and never fail to catch it. We've got an infinite game going on forever. All we need to do to work out if the throw quality was any good is just at the point at which it's being thrown, just save that state into a variable. Because we're dealing with this imperative version, we have to kind of take that moment in time and save it in a variable so that we can access it at a later point in our future set timeout, for example. So we just say that 50-50 chance it's a bad throw, and we capture that in isBadThrow variable. So that's done as well. 3 out of 4, not bad. Final point, we need to use that isBadThrow variable later on in our next set timeout to check if the ball is dropped. So we had our helper function check dropped. So we're just passing in our isBadThrow into that function, and there's a probability that if it's a bad throw, if it's a good throw, it will be caught. And if that returns true, then the game's over, the ball's been dropped. So we will stop our iteration of our recursive function calls. We've done it. That's the imperative example done. Nice and straightforward. We have seen potentially already some weaknesses of this solution, and we're going to look at how maybe the reactive solution helps us avoid some of those things. You might be thinking already, okay, we've got some nested set timeouts, so we're creating closures as we go down, we're having to pass state down, having to close over an outer variable. There's potentially some flags that we've seen already. For our reactive example, when you create reactive programs or when you create reactive solutions to things, what you're really thinking of is how can I build up an event stream to look at from dependent event streams. So how can I break up my problem into multiple small event streams and then compose them together to make a final event stream for my overall game? So essentially, we could boil it down to we need to observe somebody clicking the start button as one set of events, one stream. We need to observe the whole concept of a throw, all of that's incorporated, the weight as we throw it, it traveling through the air. We need to incorporate all of that into some observable event. And we also need to observe the catching process. So those are our three streams that we need to make up for our program. So again, just like with the imperative example, starting it off is very, very simple. RxJS, which is what we're using here, there are other libraries for reactive programming, but obviously this is Angular Camp, so it makes a lot of sense to use RxJS. It comes with the from event helper, so we can just look for a click event on our start button. And right now, we could sum up our whole game as the stream of clicks, because that's all we've done so far. So we're just going to call our game $, using that convention. And at this point, we've done nothing. Because of the nature of observables, they're a bit like functions that you've defined, but you haven't called yet. So right now, all we've done is define a function. It's only at this point where we actually start listening for those click events, because effectively subscribe is like calling .call on a function that you've defined. So this is the point at which now we're now listening for click events. What we're going to do then is just like with Todd where he showed you switch map, is we're going to switch map from those click events, so the stream of click events that are happening over time. Every time one happens, we're going to switch onto the fundamental business logic of our game here, the handle, throw, and catch between James and Todd. And the only reason that we're using switch map rather than map, for example, is because our game is fundamentally built up of observables. And switch map allows you to switch to a different observable wrapped value. You're not just taking one value and changing it to another. You're taking one value and changing it to an observable of a value. So this is how our game will look in this reactive world. We just need to build up this handle, throw, and catch logic. So this was our usage. How do we actually define handle, throw, and catch between? So in the reactive world, we still need the ability to pass in our players as dependencies. So we've got player 1 and player 2, just like with the imperative example. But this time, we're going to be starting a stream. And because we don't really care about the value, a common convention is to just use an empty string as a way of starting a stream that you don't care about that initial value. So we're just going to start that stream off. And as we've seen before, rather than recursively calling a function this time, we can just use the built-in repeat operator from RxJS. So we can just keep repeating this empty string. It's not going to do anything. But every time a button clicks, we're going to map onto this game. So we've kind of handled the first piece. How do we take it from a button click to beginning our business logic? Now we need to think about what events make up a throw. To create that overall observable of a throw, how do we take these individual events? What makes up a throw event? So let's quickly refresh our memory of the imperative example. We basically have the following points to cover. We have person 1 starting with the ball. We have waiting while they get ready to throw. We have person 1 throwing the ball. We need to capture whether it was good or bad. Travels through the air, so a slight delay again. And that's it. That's the whole throw event. We could say that the whole throw event is incorporated by winding up, releasing, and the ball traveling through the air. That's one throw. So if we could set up a way to observe that set of events as one person throwing event, then that would allow us to build up a section of our program. So we've seen already that we're capturing if the throw was bad by just using a probability. So we capture if it's a bad throw, and all we're going to do is create an observable of that value. So all we're doing is creating a Boolean, true or false, and we're just going to create an observable of that value so that we can use it in our program. To build out the rest of this person throwing the ball with those bullet points I just mentioned, we're going to start off with a stream of true or false events for whether the throw was good or bad, and we're just going to use some operators on it so that we can do our side effects of adding or removing the ball and incorporating the delays between throwing them. So we're going to start off with this Boolean. We're then going to use the do operator so that we can have the side effect of the ball being added to my DOM node. This is just going to give us a way to perform some action as the stream comes through. It's not going to change the value of the stream in any way. And then we're going to delay for 1 second. So in the imperative example, we had to wrap the whole thing in a set timeout. We had to nest all of our program. But in this case, we just need to use the very simple RxJS operator called delay. And we're going to delay for 1 second. Person 1 throws the ball, so we remove it. And we're using a do again, exact mirror image of our add. And then we delay for the ball traveling through the air again. So our whole example, once we wrap it in a function to be able to pass in which person this is referring to, becomes this code here. We're incorporating the quality of the throw, was it bad, was it good, as a stream. And when that happens, we're going to add the ball to the person that starts with it, delay for 1 second, release the ball, and wait for 1 second while it travels through the air. We've managed to capture, for each given person in this function, exactly how a throw event takes place. Because we've wrapped it in a function like this as well, we can make use of the switch map again to switch based on the logic we've just defined. So we've seen this is our usage as a refresher from before. We just need to plug in the throws into our overall game. So we've got handle, throw, and catch between Todd. We start off our stream. We're now ready to plug in our throw logic. We've got player 1 having it set up as the handler for switch map, and we've got player 2, and we just pass in the two things there. We keep repeating. So right now, we're just both throwing the ball somehow, and there's no catching in between. So all we have to do is repeat the same process for throwing. And we've already encapsulated most of our program in the throwing logic, so the catching is actually remarkably simple. All we need to do is use that Boolean value to check if we dropped it, just like in our imperative value. And this time, we're going to, if we've dropped it, we're going to return an observable that errors immediately. One of the qualities of observables is that they have these 3 core events that they can emit, effectively. You can have a next value. You can have a completion of the stream, so no more values from that producer will be produced. And you can also have an error event. And by using this throw static method on the observable, we can create an observable which immediately fires its error event. And so this will have a cascading effect and kill the whole game because the ball has been dropped. If it's not been dropped and we caught it successfully, again, we're just going to create an empty string stream that we don't really care about the value. We're just going to add our ball. So this will keep the stream going, and then we'll kick into our repeat, and so we'll keep going. So if we successfully caught it, the game will keep going. So all we're going to do, just like with the throw, we're going to wrap it in a function just so we can pass in that person so that we don't have to duplicate the code between Todd and I. We can just pass in a person. And so we have our function, which will take in our isBadThrow and be used inside of a switch map, because the only thing we need to worry about in a switch map is returning an observable. So we're returning an observable from both of our different values, one that errors immediately, one that doesn't. And then all we need to do is plug in the catch functions. So we have handle, throw, and catch between, and we have throws, catches, repeat. And this is one of the great qualities of reactive programs, is when potentially you could see it as a little more work up front to conceptualize the different events of your program. But once you've actually done that, once you've actually put the effort in, your programs become very, very readable and very, very declarative rather than having to fiddle with things in an imperative way. You can pretty much read what this program does, and that's one of the great advantages. So that's our 3 dependent events. We've built up our full reactive example. One of the things I briefly was going to talk about was the idea of where would we go from here with these different examples. If we wanted to add a new feature, for example, Todd and I are throwing the ball, and right now it stops if we drop it. That's nice and easy. We've coded that. But what would it be like if we also said that we throw and catch the ball until David yells stop? That is another way that the game could end. In our imperative example, we would have to add another variable or another function which tracks whether or not David has yelled stop yet. And every time the game could possibly stop, we'd have to check, was that piece of state true or false? Has David said stop? Has David said stop? We'd have to exit our program at different points in that nested set timeout. In the reactive version, all we would need to do is create a new event stream of David yelling stop, and we could then use the take until operator, which many of you might have seen in your Angular programs, because that just gives us a way to kill our event stream if another event stream emits a value. So often with these reactive programs, if you spend a little bit longer mapping out the different event streams, it can really pay off in terms of the future and adding new features. So that was the core concepts we wanted to cover today. We've looked at the observer pattern in general. We've looked at producers and consumers, and a push-based model of producers going to consumers. And then we've looked at a little fun example of throwing and catching a ball from the Friends episode to highlight how you might approach different things in different ways. In an Angular world, we have to approach things in an imperative and reactive way a lot of the time because we have a number of different things which were built with reactive programming in mind, but we still have a lot of things which weren't. So we have to deal with our templates. Often we have the async pipe for some reactive programming, but often getting things out of our templates is not so reactive. So there will always be a mix and match. We're not saying imperative is bad and reactive is good, but it's often worth thinking about, is there more than one way to skin a cat, more than one way to solve a problem? Thank you very much.
Thank you, everyone. Thank you.